RRU versus AAU, the two units powering modern mobile networks. There is a quiet battle happening on towers all over the world. You cannot see it from the ground. It does not make headlines. But every time a mobile network operator decides how to build or upgrade a cell site, they face a choice that shapes the performance, cost, and future of that site for years to come. The choice is between two pieces of hardware: the RRU, remote radio unit, and the AAU, active antenna unit. Both sit at the top of a tower. Both handle radio frequency transmission and reception. Both connect to a BBU at the base of the tower. But they are built differently, they perform differently, and they are suited to different deployment scenarios in ways that every telecom engineer needs to understand. What the RRU is and how it works. The RRU is the radio unit that transformed base station architecture when it replaced the traditional BTS model. Before the RRU existed, radio hardware sat in a cabinet at the bottom of the tower, and long coaxial feeder cables carried the signal up to passive antennas at the top. Those cables caused significant signal loss, wasted power, and created maintenance headaches that engineers lived with because there was no better option. The RRU changed that by moving the radio hardware to the top of the tower, right next to the antenna. A short jumper cable, just a few meters long, connects the RRU's antenna port to the passive antenna above it. The signal loss across that short connection is negligible. The full transmit power reaches the antenna and goes into the air. The RRU connects downward to the BBU in the equipment cabinet through a CPRI fiber link. The BBU handles all digital baseband processing and sends digital signals up to the RRU. The RRU converts those digital signals into radio frequency signals through modulation, amplifies them, and transmits them through the passive antenna. On the receive side, it does the reverse, capturing incoming signals, amplifying them, demodulating them, and sending digital data back down to the BBU. The passive antenna that works alongside the RRU is a separate physical unit. It has no active electronics inside it. It is a carefully engineered array of metallic elements shaped to direct radio energy in a specific pattern, covering a sector of perhaps 65 or 120 degrees horizontally and a defined tilt angle vertically. The RRU drives the antenna, but the antenna itself is passive. It only shapes and directs the energy the RRU provides. What the AAU is and how it works. The AAU, active antenna unit, takes the relationship between the RRU and the antenna and collapses it into a single integrated unit. Instead of a separate RRU connected by a jumper cable to a separate passive antenna, the AAU combines the radio hardware and the antenna elements into one physical device mounted on the tower. Inside the AAU, there are active electronic components, amplifiers, transceivers, digital processing circuits, working alongside a large array of antenna elements. In a massive MIMO AAU designed for 5G, that antenna array might contain 64, 128, or even 192 individual antenna elements, each connected to its own transceiver chain within the unit. This configuration, known as Massive MIMO, allows the AAU to form and steer narrow beams of radio energy toward individual users rather than broadcasting energy broadly across a sector. This beamforming capability is one of the defining features of the AAU and one of the primary reasons it was developed. In a traditional RRU and passive antenna setup, the antenna radiates energy in a fixed pattern. Every user in the sector receives energy whether the network is actively serving them or not, and interference between users sharing the same frequency is managed through time and frequency scheduling rather than spatial separation. In an AAU with Massive MIMO, the system can serve multiple users simultaneously on the same frequency by directing separate beams at each one, dramatically improving spectral efficiency and overall network capacity. The AAU connects to the BBU in the same way the RRU does, through a CPRI or eCPRI link running down the tower. From the BBU's perspective, the interface is similar. The major difference is what the AAU does with the signals it receives from the BBU, and how much more it can do with them compared to a conventional RRU. Comparing size and weight. This is one of the most practically significant differences between the RRU and the AAU, and it is a difference that every tower engineer feels immediately when they arrive on site. A typical RRU is a relatively compact unit. Depending on the vendor and the frequency band, an RRU might weigh between 8 and 15 kilograms and have dimensions roughly comparable to a large briefcase. When you add the passive antenna it connects to, you are adding another 10 to 20 kilograms and a panel that might be 1 to 2 meters tall. The total installation involves two separate units, the RRU and the antenna, each mounted independently and connected by a jumper cable. An AAU is significantly larger and heavier than a standalone RRU. A 5G Massive MIMO AAU can weigh anywhere from 25 to 40 kilograms or more, depending on the number of antenna elements and the power output. Its physical dimensions are dominated by the antenna array, making it a large panel, sometimes approaching 1 meter in height and half a meter in width, with all the active electronics integrated behind the antenna face. The weight difference has real implications for tower loading. Every kilogram mounted on a tower adds to the structural load that the mast must carry. Before deploying AAUs on an existing tower, structural engineers must assess whether the tower can handle the additional weight. In some cases, towers built in an era of lighter passive antennas and standalone RRUs require reinforcement before AAUs can be installed. This is a cost and timeline consideration that operators must factor into deployment planning. Comparing installation difficulty. Installing an RRU alongside a passive antenna is a well-understood process. Tower engineers have been doing it for years across millions of sites worldwide. The RRU mounts on the tower structure, the passive antenna mounts above or beside it, a short jumper cable connects the two, and a CPRI fiber cable runs down the tower to the BBU. The process is methodical and the skills required are well established in the workforce. Installing an AAU is more complex in several respects. The unit is heavier, which makes handling it at height more physically demanding and requires careful rigging to lift it safely to the mounting position. The integrated nature of the unit means there is no separate antenna to align independently. The entire AAU must be positioned and aligned correctly as a single assembly, which can be less forgiving than the two-step process of mounting an RRU and antenna separately. The AAU also requires more careful alignment precision because of its beamforming capabilities. The performance of a Massive MIMO AAU is sensitive to its physical orientation. Azimuth and tilt must be set accurately during installation, and any deviation from the planned position can affect coverage and capacity. Some AAUs include built-in sensors that report their physical orientation to the network management system, which helps engineers verify correct installation remotely, but the initial physical positioning still demands care. Cabling at the top of the tower is simpler with an AAU because there is no jumper cable between the radio unit and the antenna. That interface is internal to the AAU itself. This removes one potential failure point and simplifies the external cable management at the tower head. However, the power feed to the AAU must be capable of supplying the higher power consumption of a Massive MIMO unit compared to a standalone RRU, which can require upgrades to the power infrastructure at some legacy sites. Pros and cons of the RRU. The RRU has several significant advantages that explain why it remains widely deployed across 2G, 3G, and 4G networks and continues to be used in 5G deployments where Massive MIMO is not required. Its first advantage is maturity. The RRU architecture is proven across decades of deployment. The skills to install, configure, and maintain it are widely available in the engineering workforce. Spare parts and replacement units are readily available from multiple vendors. This maturity reduces risk and simplifies operations. Its second advantage is cost. A standalone RRU paired with a passive antenna is generally less expensive than an equivalent AAU. For deployments where Massive MIMO is not necessary, rural coverage sites, low-traffic suburban areas, indoor solutions, the RRU delivers the required performance at lower capital expenditure. Its third advantage is flexibility of antenna configuration. Because the RRU and antenna are separate units, operators can choose different antenna types for different coverage requirements without changing the RRU. A wide-beam antenna can be swapped for a narrow-beam antenna on the same RRU if coverage requirements change, without replacing the radio hardware. The primary disadvantage of the RRU is its performance ceiling. A conventional RRU driving a passive antenna cannot perform Massive MIMO beamforming.